to be here. I thank the organizers, and I thank you for people who are here. So I'm talking about the this one. So this work is in collaboration with Dr. Hino. I am from Japan, and he is also from Japan. So now I'm talking about this one, which is about master equations and some geometry and some expectation variables. So I'm talking about motivation and background first, and then after that I'm talking about review and main claims in details. And I want to conclude my talk at the end. So I want to talk about motivation and the background. So in the literature, the master equations have been studied by physicists mainly, and metric contact geometry have also been, have been studied by mathematicians, and the contact geometric thermodynamics by many people, including the talk before, and information geometry by many people. So, okay, fine. There are many studies here. Here. So our aim is to combine theories above, so that we can apply theorems from here to there to here. So if you have such a nice theory, we can exploit, we can use such a theory, and then we can understand everything, hopefully. So this is, if you have this theory, everyone is fine. So everyone is happy. So I'd like to find this kind of a unified theory, if I can. So this is what I'm going to show in this talk. So what are master equations? Master equations are equations like this, So these equations describe the time evolution of P, which is probability T at the state J at time T. These equations are very important for developing non-equilibrium statistical mechanics. And these equations show relaxation to the equilibrium states. And these equations could be integrated to obtain average objects. So this is P. So if you integrate all over the state, you could have something like thermodynamics. So these kind of equations are called master equations. How about the B here? This one appear in here. So maybe you are not familiar with this jargon here. What are these metric manifold? These have been studied these are studied in math. So, but what are the roles of this metric manifold for non-equilibrium mechanics, non-equilibrium statistical mechanics, and the relations among master equations and this kind of metric manifolds and the contact manifolds are not so clear for me. So, okay, these are known facts. These are my questions. So we would like to answer these questions here. So these are my questions. And by focusing on 1 and 2, 1 is the dynamics of expectation things derived from master equations. Master equations for P, and then you sum over all over the state, and then you have this kind of expectation, these values, and then you can make it. You can make it. You can. And okay, so I wanna study its geometry. By doing so, unified theory is shown. This is what I'm going to say in this talk. So our statement in this talk is the following. A toy model is shown. So I can't do everything. So I want to show just the one model, which shows what I want to show. And to do that, I choose this W. So I want to explain. I'm going to explain it later. But I'd like to choose this kind of things, and I'm also going to show this line dynamics is obtained, and then without this dynamical system is derived without any approximation for my toy model, and then this is this system is described on contact manifold, and it's this manifold. And then I want to show you the how this dynamical system is going to equilibrium states, and this can be described by information geometry. So these are what I'm going to show you. So this is more or less how I explain this model. So what I'm going to show you is summarized like this. In statistics, you have this equation, master equations. After the long time limit, you get this distribution function. And this can be integrated out to have this kind of a system. So this one denotes the sum over the states. And this is the dynamical system, and this can be described by contact Hamiltonian systems. Okay, and these guys are going to be equilibrium states, and this, okay, from the geometric viewpoint, this is like a Legendre sum manifold. These boxes are equivalent to information geometry. In this talk, I want to talk about these blue lines. Okay, so what I'm going to show you today is to show these blue lines. So a toy model, as I said, I can't do many, what I can do is just a model, using a model. So this is what I'm going to talk about. So my model is as following. So okay, rough sketch of the how to have my model. So okay, we choose the distribution function, which is like this, not continuous but discrete. So we construct master equations like this. So the left hand side is dp dt, and the right hand side depends on state j. And then you define the two types of expectation. So for one which is non-equilibrium one, which does depend on time t, and for the other one does not depend on time t but defined at equilibrium. And then you get the dynamical system from 2 and 3, and this is the equation motion for P. This is the expectations. So from this one, we get dynamical systems for dynamical systems. So this is these are master equations, one, and big gamma denotes a set of discrete systems, and T is a time. So these are master equations. P dt is like this. So for the state j is in between t and t plus dt, and this p is normalized like this, and this one is describes this one. So if you have a state j prime, and then you can find p j prime t, and then this is going to be p with this rate w j prime. Okay, if you are in here state j, and then with p j t, and then this is going to be j prime with the rate this rate. So okay, so this is our model. The thing is that we need to choose this guide. So okay, so this is very important. We choose this w, and then you get the master equations. So the thing we should do is to choose w. So we choose this guy like this. So this is our equilibrium distribution function depending on theta. Theta here is a set of real numbers specifying p at equilibrium. So this does not depend on this guy, J prime. And this depends on theta, so we write in this way. So you choose this guy, and then you get this master equations. Forget about this bit. So dp dt is like a minus p. So this is like a minus, the solution is like a exponential function, okay? And then, in fact, you can show this p after the, okay, in this limit, this p is going to be at equilibrium. Very easy to show. So, okay, what I show you is to choose this guy, and then I get this equation motion, and then you get this limit. So after that, you get okay, you define the average 1, average 2, and one of which is depending on t. And so, okay, sorry, I'm sorry, the OA is like a function from the state to the real number. And then you define two averages like this and this one. And then because we get this asymptotic limit, we get this kind of limit, of course, and then everything is fine, should be fine. So, okay, you also define free energy like this. Okay, you define this dimensionless free energy minus negative energy. So, okay, for this P, and then you also extend this guy into the non-equilibrium state. So, if P is at equilibrium, this is 1, and then because of this one, this bracket is unity. So, after okay, if T is very big, and then this is going to be unity, and then psi is equal to psi equilibrium. So we define this one, psi equilibrium, and we also define, sorry, this should be defined psi, and then I can show that this relation holds. And then we can say this one is very important in information geometry. So, as I said, this guy is very important. So this induces Riemann geometric, and this induces two connections, this one and this one. I don't explain any detail, but this guy is used in information geometry a lot. And this guy is a convex function that allows us to discuss this duality. And this guy is a dimensionless free energy like this. So this psi equilibrium is, and this free energy is related like this. Okay, so everything is fine. We started from master equations. We get the information geometry so far. So the equations motion are obtained like this. So let theta be n real numbers. And then, of course, this does not depend on t by definition. And this guy, okay, and then I get this equation and this guy. This psi is a non-equilibrium free energy. And this guy, so I want to show how I obtain this one. So this one, if you do this calculation, by definition of the average, you get this one. And this one is from master, so by using master equation, you get this one. And then again, you use the average, you get this one. So this is something like a dynamical system. And you also can show this differential equations. Okay, from master equations, okay, I use master equation here. So this is the something like a phase portrait. Theta does not depend on time t, so the flow is constant along this line. And then this guy, the average of all, is going to be the equilibrium point. And the free energy is also like this. So theta is constant along, constant in t. And then this guy is going to be at equilibrium state. So this is something like a phase space. And then along this line and this line, you can use information geometry. So, and the psi is something like a convex function, and the form should be like this. Okay, and then I want to make it on the contact manifold. So theta, we define this kind of things, set of things. So theta 1 to theta n, and O1 to On average the psi, and then you define one form like this, and then the equilibrium point is defined like this. Okay, so if you have known the contact geometry, you immediately find this is a contact manifold, and this guy is the so-called Legendre submanifold. Okay, starting from master equations, we define this guy, and we also define this guy, and then we can define this lambda, and then we have constructed this contact manifold. And the equilibrium state is at this state. So, okay, sorry, I should be hurry. So, and then I can define the closed dynamical systems. Sorry, I need to be hurry. So, the closed dynamical system is expressed as a contact Hamiltonian systems. And then you define this big G, which is a metric, and then at the equilibrium, this is going to be Fisher metric. And then you can define the distance between the equilibrium and your non-equilibrium state. You can define this kind of a measure and length, and then this can be shown as this estimate. So this is what I have done. And then what is the question? So example, is there an example? Yes, I can have. So this is the spin model, which is the Ising spin model. You can define this P equilibrium, and then you can define this Hamiltonian and this the free energy. And you can also have the master equation like this, and then everything is fine. So this is what this is a very simple example. And then we can extend this to this very strange quantum manifold. So I can't say, so because things are very messy, I don't explain, but you can introduce a 1-1 tensor, vector field to vector field, and the lambda which is like a contact one form, G is like a red vector field. So I don't explain it detail, but if you have the, okay, this is like the extension, the extension of the contact manifold. So this guy introduces big G, and this big G induces this kind of contact manifold. So I don't say any detail, but yes, this can be done. And the important thing is to introduce. Okay, so this is what we have found. Our dynamic system shows the relaxation and the contact vector. So this can be written in terms of contact vector field, and then you can find small h, which is a contact Hamiltonian. And then, of course, this is not a conservative system, so you've got this one. However, if you use this 1-1 tensor acting on xh is your contact Hamiltonian vector field, h is conserved. So, but I don't know the meaning yet. So this is what we have found. So my conclusion is we show some model, and the geometric view is established, and I can show this kind of how I have done this kind of a picture. Thank you for your attention.
Thank you very much.